So, Vanakkam. So, we will continue our engineering seismology lecture, recapping the last part. So, this is the part 8 actually. So, this recapping, as I told you that, so the next class onwards we are going to talk about basically how you can effectively predict this earthquake hazard. Okay. So, the prediction of this earthquake hazard will help you basically to design a new structures as well as retrofitting the existing structure, also plan like how many houses will collapse, okay, what is going to happen and how many facilities you need. So, basically the disaster management and planning. So, in this actually we have seen that, so the whatever the knowledge so far we have gained, okay, or interpreted, okay, the seismic wave, okay, the earthquake is actually measured, okay, so are recorded in the form of the seismic waves. This wave amplitude, duration, frequency contents are useful for the to represent how this wave will behave. Okay. For the any engineering application, okay, so basically we need a complete information to estimate a force, okay, force caused by the particular earthquake. So, the prediction of the earthquake hazard, okay, basically will focus on getting this waveform what you get. Okay, so this waveform, because since we don't have the many recorded earthquake data, so this waveform prediction, or as we have seen that here the values, okay, so the PGA, PGV, those kind of prediction also is there, or you can also get a spectrum, okay, so response spectrum, frequency spectrum, okay, that. So, this kind of information we needed for the engineering application. So, our objective is basically estimate these parameters very accurately and reliable manner. That is what we studied, the understanding of this subject. So, today class we are going to see the source parameters, source characterization, which we have discussed in detail earlier, and then a simple models which used to arrive your amplitude part like peak ground acceleration or peak ground velocity at a particular location, or a stochastic simulation where you can simulate a acceleration timesty of the data at a particular location. So, these are all the aspects we will be seeing today recapping class actually. So, the source mechanism means what type of fault it is. Okay, so what type of fault means like the normal fault, reverse fault, thrust fault. So, those things we discussed. So, how much the compressional tension and shear forces are created in that particular earthquake will be used to say that. So, particularly if you look at that, this is a typical earth picture where the earthquakes are occurring, the faults are rupturing. So, then depends upon this rupture, so the compression and tension wave propagates all around direction. So, you have the seismometers recorded kept at a different place. This records its a compression and tension force. So, this part, okay, the shaded part, okay, so basically compression and white part is a dilation tension. So, then it forms some kind of shape, that shape, okay, represents a beach ball. Okay. So, the source mechanism is represented as a beach ball. So, the beach ball basically a ball which is having a stripe of colors, stripe colors it has basically. So, here the black and white is produced to represent a beach ball. So, this beach ball diagram is unique for a particular type of source. For example, the normal faulting you get a beach ball similar to this. Okay, this is the beach ball for the normal faulting system. You can see a compression, tension, alternate shaded part. Similarly, the thrust fault you will get a beach ball like this complete thrust fault. So, where you can see this one. Okay. So, the normal fault and then reverse faulting system. Okay. So, then similarly the strike slip. Okay. So, transverse fault will have the different kind. So, the combinations also will have. So, this is the typical case where the easiest way to understand is given, but in the real earthquake this shape may not be the similar, it may be a smaller, higher, depends upon the how the compression and tension force take into share. Okay, so this kind of representation is actually a source mechanism derivation or source mechanism arriving. So this part generally seismologists they get okay data from the different earthquake record and then identify a tensile and compressor source and prepare this diagram and release that along with the source earthquake information. These are very useful to future to predict that this one kind of things. Okay, so then apart from this we have seen that there is a simple source models okay which is works based on the energy release concept in the tectonic fault will help you to identify how the peak displacement or acceleration or velocity varies with the distance. Okay, so this is basically assumes here the wave travel at a particular location spherical form and then the time delay between the arrival of P and S wave. So then that velocity is taken into account and then there is a amount of energy transmitted location away from the source decreases with the distance. Okay, this total energy okay wave front equals to the energy less okay happens due to the loss due to the heating of that medium and then followed by that plane. So which is proportionally to the your distance. Okay, so this concept has been extended and try to arrive how the amplitude at particular location using the point source model and planar source model. So the point source models are used for the magnitude which is magnitude 5 and less. The planar source model used for the magnitude which is 5 and above. So here they consider each grid of the plan area as a point and then finally they integrate. You can see the difference between the this length and width is incorporated here. So here there the length and width is not incorporated. Okay, so the 4 pi and all accounted to sphere shape of the earth. Okay, so this kind of models are very much useful to compare okay, realistically validate what kind of pattern of this seismic wave travels at a particular location. So the even we have seen that there are typical case studies people have taken the data and try to estimate using this kind of simple model and observed data and try to compare and fitting the data and try to arrive how the patterns are going. Okay, so that was analysis are done. So this quite these simple models are very useful for several cases. Only thing these simple models are assume materials are homogeneous okay, and then uniform throughout the region which is not practically possible. That is why you may have some bias. Okay, so that bias some places is acceptable because of the smaller variation, some place it may be having the very large variation. Okay, so those kind of things has to be taken into account when you use this model. Okay, so this is the way you can get a time domain parameters from the models. Okay, so this is a simple model which accounts the wave arrival time and then the energy release and equating them you will get your peak ground acceleration, peak ground velocity. So from this kind of analysis generally it is found that the hypocenter okay, the hypocenter measurement is more reliable to represent a variation of the acceleration values than the epicenter. That was the major findings from this kind of model analysis. So the next is, so this is the peak ground acceleration, a simple model which gives this data. So another is as I said that so this peak ground is a single value. So if you want to understand how the waveform, complete waveform, its frequency and duration, you need a acceleration timesty data. Since all the location we do not have the recorded earthquake data, people developed a simulation ground motion models. Okay. So simulation of ground motion, this was done by basically Bohr okay, by segregating the source, path and site parameters. So as we have seen that the any waveform at a particular location controlled by the source property and characteristics okay, like the rupturing direction, rock properties and then where it travels, path characteristics and how it reaches site characteristics. So in this simulations model predominantly used on the rock side. So because of that the soil based characteristics are given less important. It is also very difficult to simulate, as you know that soil varies spatially considerably, but rock does not vary that much variation. So modeling of source, Okay, then path characteristics accurately, one can get a simulation model. This simulation model was basically developed by a Bohr 1983. Okay, so yeah, where he take total spectrum ground motion recorded at any site is the function of source, path and site characteristics. So we have discussed what is the source, how it affects. Basically the source is controlled by the your corner frequency and seismic moment. Path is controlled by the distance as the function of frequency. Okay, the site is controlled by the diminishing factor. So as we have seen that MW, moment magnitude related to the m naught. So if you assume what is the magnitude required, you can get here what is the seismic moment that will be feeded here, and then the r, where if you assume a location you can r. So this how much decay, damping factor, Koda wave factors, all those things are gone into the equation of the source path. So that solving up equation will get you the your acceleration time is at path. So this entire simulation is actually divided as a 5 major part. Okay, one is that generating the white noise equal to the duration of the motion obtained from the corner frequency, filter the noise by applying a Gaussian window, and then convert the windowed noise to a frequency domain by FFT for Fourier transformation, normalize the obtained Fourier spectrum with the square root of mean squared average Fourier spectrum. The normalized spectrum is then multiplied by a ground motion spectrum. They again converted to acceleration time domain by inverse fast Fourier transformation. So these details basically give you the simulation of data. So this can be explained by this or explained earlier. So using this simple diagram, so where you can get a lot of noise, this one, and then apply a Gaussian filter and then transform to Fourier amplitude. So then the Fourier window noise, the filtering is there, then the normalized spectrum, finally you get a acceleration time representing the your regional source characteristics. Okay. So the regional earthquake character is reflected in this. So this is a very useful data whenever there is no recorded earthquake in the region. Okay. So there is no instrument in the region. So synthetic ground motion data are useful for the design future level. Okay. So this is how the Bohr model become a more and more famous. Okay. So more and more popular. So this model actually the Bohr was the first person who developed this model. So he was a scientist at USGS. Okay, United State Geological Science. Okay, USGS. So where they actually come up with the first model called SMSIM model. So then later his students are modified those model with then it is called as a FinSim and then XMSIM. Okay, the FinSim was Brensov and Atkinson developed. So XMSIM was developed by the Motesidia and Atkinson. So in 2005. So all these models are in use. So each model is has its own advantage and disadvantage. We will be discussing now. So the SMSIM model, the earthquake ground motion will be treated as a rupture at a single point. The model is a white noise window using Gaussian window similar to the steps given earlier. It is useful to simulating ground motion at a distance much larger than the rupture dimension. So this is basically the rupture dimension should be smaller, the distance should be larger. So this does not take into the fault type into activity. So fault consideration. So because of that there are some limitation. For example, it cannot capture the directivity effect of the fault, cannot capture the rupture heterogeneity, cannot capture the fault geometry. So these are all the limitations of the value, but still these models are very well work up to the magnitude of 7. Okay, so that is the highlight of this model. Somebody want to synthetically generate a earthquake where the stable continent region where the expected earthquakes are lower in magnitude, like below 8. Okay, so this model will be more suitable as it works up to 7. But above 8 magnitude you cannot use SimSum because there is a controlled source and path parameters which is modeled in the FinSim. So the entire rupture area will be divided into number of subfault. Each subfault will be treated as a single point source model with omega square spectrum. Contribution from each subfault will be summed up and sufficient delays depending upon the rupture velocity and the subfault size. Useful to estimate a total slip distribution on the rupture area to understand directivity effect. So this basically needs regional parameters such as a strike, slip, dip, stress drop, rupture area, geometric spreading, kappa factor and strength factor. These are all we discussed earlier. Those parameters are very important, and here actually the simulation depends upon the subfault size. This is the one of the major limitation of this particular method. So that's why the people scientists start working on the updating that. So the same Atkinson group, so where they created model called XSIMSIM. So the XSIMSIM overcome the limitation of the FinSim, okay, so which is developed by the Motazidian, Atkinson 2005, introduced the concept of dynamic corner frequency, which will make a simulation independent of the subfault size. So FinSim use conservation total mass when the sum up the subfault event size, or XSIM uses the conservation of energy using the normalized velocity spectrum. So the duration and motion does not depend upon the stress drop was in the FinSim. Each subfault will be modeled as a point source and the summation at interest will be done with suitable time. So the XSIMSIM is the most robust way of simulating the ground motion data. So as I told you that simulation of ground motion data itself a topic of PhD research, because it's not that simply, even though the models was universally developed only few models, it is not that you simply take that model and use. You should know how to use that model effectively, and using that model what you generate, how it is useful, that data how you can convert it into the ground motion prediction equation and other predictive equation. That's why the simulation models are very important. As I told you that very few people work on simulation models in India. The first student who worked on the simulation model is Raghukant, okay, then followed by the Abhishek Kumar, okay, so my student, and I also did something, and then my other student Ketan Bajaj. So these are all the people who worked simulation of the ground motions, and followed by using that simulated data to get the other ground motion prediction equation and things like that, which is very much essential and needed for the seismic hazard analysis. So this is the typical recorded data, okay, so using the SMSIM and the FinSim and XMSIM at the magnitude of 7 and then the kilometer. So you can see how the sources are assumed in the SMSIM, the single source with larger size is assumed, so which is reflected like this. So in the XMSIM, FinSim, several segment of the source is assumed. So each one rupturing is happened like that. At the end of the day, all these data are clubbed together and finally arrive the bigger earthquake what you are looking for. So this is how the difference between the SMSIM and the SimSim model, which is useful to get a synthetic ground motion data. So this is the another case where we have done a typical Indian earthquake simulation using the available source parameters. So some of the earthquake where there is no such parameters are available. So we range, okay, we adjusted the values by parametric analysis and tried to match recorded and then observed. You can see the Indo-Bangladesh earthquake, so during 1988 and 1991 Uttarakashi earthquake, so the actual and synthetic. So these data is only further used to derive a spectrum of those earthquakes. From there it is went to develop a ground motion prediction equation. Okay, so ground motion prediction equation. The ground motion prediction equations are the type of predictive equations, okay, which is useful to get a peak ground velocity or peak ground acceleration or peak horizontal acceleration or peak horizontal velocity. That is the ground motion prediction equation. You will get a time domain parameters as the function of m and r, the other factors which is easily obtainable. So this is about the simulation of the earthquake. As I told you that we have been simulated large number of earthquake and using in our research. So the next part of that. So, as I told you that the objective of this is to estimate a hazard. To estimate a hazard, you need some kind of function apart from this model, which is very complicated, very limited people can use. So, the functional form which predict a hazard. Okay. So, that kind of functional form is called as a predictive relation. Okay, the predictive relation is basically is the function of m and r, some other parameter depends upon the region. This functional form, okay, is very much useful to estimate what is the future expected similar kind of duration, amplitude, intensity. Okay, so those are all the parameters. So that's why the predictive relations are very important in engineering seismology, particularly the next process onwards we will be handling those kind of things. So this equation development has to be done systematically. So, okay, so the each place the predictive equation functional form should be different, depends upon the their regional data, it has to be arrived a best suitable form. So, the universal prediction equation model is given here. You can see the 1, 2, 3, 7 up to 7. So, each component represent some kind of natural phenomena happens at the earthquake. Okay, what happens in the earthquake is represented here. So, the y, okay, all the predictive equation first one is always logarithmic function of the this one. Okay. So, and also we have also seen that the magnitude also varies in the form of logarithmic base 10. Similarly, ln, and then the other parameters take care of the magnitude and source and its variation and then its movement, all those things are modeled in the this form. So, this form some constant may vanish when you check its suitability for a particular region. Okay. So, people have developed a large number of predictive equations throughout the world, which has been summarized by the Douglas 2019. Okay. So, he has prepared since 2004, he has been preparing this predictive equation datas and models and try to understand how the predictive equations are going. Okay, so here you can see that as I told you that he compiled all the predictive equations, about 468 empirical ground motion predictive equations are available to estimate peak ground acceleration like PGA and PHA, and 300 models of the predictive elastic response spectrum available to estimate a spectrum, okay, for different time period. So, the Arias intensity 32 models are available. Okay, the cumulative absolute velocity 10 model, Fourier's amplitude 18 model, maximum absolute amplitude 6, inelastic Japanese spectra 5, Japanese meteorological agencies 4 intensity model, and then macro intensity model 50, commonly called as intensity prediction equation. The mean period model 6, peak ground velocity 137, peak ground displacement 35 and relative amplification 17 and vertical to horizontal acceleration to 12. So, these are all the number of model which is together comes as a big volume of book. So, which is published in this link. If you see this link, you can download these books and data which will be useful for several applications. So, this predictive model, okay, so as I told you that each region there will be 100 sub predictive models or few predictive models. So, you have to identify what are the predictive models available for your region. That model is how useful to interpret your or estimate your predictive value. So, there are intensity predictive equation, duration predictive equation, peak ground predictive equation, peak ground velocity predictive equation, peak ground displacement predictive equation, peak ground acceleration, okay, that is predominantly used at several places. So, those predictive models are actually very well used in the several application. So, this give summary of all those equations. As I told you that even though India has very long history of earthquake, the number of model, okay, the number of conversion equation, number of anything related to this prediction like intensity model, duration models are very, very limited. We can also remember here that the predictive equations developed for the peninsular India may not be applicable to the North India. Why? Because that seismotectonic, okay, and seismic activity of the region. So, if you do mismatching this kind of equation without a systematic procedure, the result what you are giving is actually useless, it may not be required at all. So that we have to remember when you are talking about the predictive equations. So but all this summary of equation you can find. So India, for the peninsular India, we have very few predictive equations, okay, which is basically around like maybe 4 or 5 equations you can find, and intensity equation only one is available. So North India considerably you have the good number of predictive equation, but still those equation applicability for the wider magnitude distance are again question. So in order to overcome that, in our group also we have done a synthetic ground motion, and then we also develop a predictive equation considering both the data as well as the owner of the data, so that the issues can be solved amicably. These predictive equations are identification based on the locations are very important. You cannot use a Kutch equation in the Jabalpur, you cannot use Kutch to the Uttarakhand. So something like that, there is a considerable difference in the seismotectonic, okay, the wave magnitude size, and then how this waveform reaches at a particular location, which is precisely modeled in the predictive equation. So this predictive equation, okay, so the understanding of predictive equation, selection of predictive equation itself a separate topic we will be discussing in the coming classes for the hazard estimation. So when you talk about the predictive equation, what about the predictive earthquake, prediction of earthquake? So can we predict a earthquake? If the earthquake is predicted, what will happen? So generally if you predict a earthquake, it is very nice because you can minimize lot of people dying, okay, like you are forecasting tsunami and storm, no, people will move. That is the one thing, it's a very big advantage. But then if you have to predict a earthquake, so okay, so what are the parameters which you can see, how reliable that parameter to get a more accurate prediction. Accurate prediction means the earthquake should tell where exactly the earthquake will come. Earthquake prediction should tell where exactly the earthquake going to occur, how much the size, okay, so that is also very important, and then what time, where, size and time. These are all the three major challenges in the prediction of the earthquake. If you understand how the earthquakes are occurring, okay, so the prediction of the earthquake is not a very difficult, and we will understand that the prediction of earthquake is not that easy as the understanding of the source, and then the stress building is very complicated. If you understand that very well, how much of stress is built, how is moving, what is the geological age, then you can predict the three parameters, which is very challenging. So this prediction of earthquake and then the associated problem, even if you predict the earthquake, what is going to happen, how far it is the knowing and not knowing the earthquake going to occur will impact at a particular place, like socio-economic problems due to the prediction of the earthquake. Prediction of the earthquake due to that will be discussed in the next class. So with this, I thank you very much for watching this video on this recapping of all the class notes. So I hope you might have understand many parameters which is useful, and then also we recapped so that even some of the classes you missed you can see here. So we highlighted all the most important, which is exam point of view, as well as the understanding the subjects also very important. So if you have any questions, all those things basically you can write to TA or me, or call TA or me, so that we can try to rectify your questions, okay, which is technically sound, not somebody is taken your work and publishing somewhere, not that kind of social unrelated questions should not be handled during the assignment period, okay. So thank you very much, we will see you in the next class.